My friend needed a car, so mine I lent him. He got in a crash, the fenders he bent them. I used to have dollars, but on repairs I spent them. All my cash was lost, but what was saved was momentum. If you don't own a pool table, it's easy to rent them. You'll see the pool balls plating in all directions. Momentum's a vector, so X and Y, don't neglect them. Again, you'll see conservation of momentum. Now, impulse is the average, force times time. F delta T is the impulse definition rhyme. When a bat hits a baseball, it might just dent them. External forces cause a change in momentum. Now, if you got complaints, you can definitely vent them, but the things I just said, I definitely meant them. Hamlet slings and arrows, by opposing you can end them, or just go with the flow. Conservation of momentum, yeah! So let's begin with a definition of momentum. Momentum is defined as, and we use the letter P for momentum, and there's actually some controversy about why P is the term or the letter used for momentum. One belief is that Hamilton, when he reformulated Newton's laws, he used P, so that's what stuck. Some people say, well, M was already used for mass, N is a counter number, O looks like a 0, P was the next one. But whatever the reasoning, we use the letter P to represent what Newton called the quantity of motion. In fact, Newton used the concept of momentum exclusively. He didn't use mass and velocity at all for his second law of motion. He used momentum. And let's just define what momentum is. It is a vector, so that we have momentum in the x direction being m times v sub x. Momentum in the y direction is m times v sub y. Momentum in the z direction, m times v sub z. It is a vector. The components are independent of each other. So here's how this applies to Newton's second law. We know Newton's second law as the net force equals ma. If you're using calculus, that means that the net force is the mass times the dv dt, the first derivative of velocity. If you're in the physics 1 or 2 class, every time you see a d, just substitute a delta that goes to 0, a very small delta, and it'll work for you. This is simply the derivative of mv dt, meaning that here's how Newton actually formulated his second law. He said that the net force on a system is the rate of change of what he called the quantity of motion. So this is another way of looking at Newton's second law, that the forces acting on an object are simply causing a change, the rate of change of the quantity of motion, which has to do with mass and velocity. The rate of change of momentum. So here is Newton's, we typically rewrite this as this. The net force times a small amount of time equals the change in momentum. And that's how we would do it if you're not using calculus. This part on the left, F delta T, is called the impulse. And the part on the right is the change in momentum. Notice that the impulse is not equal to momentum. It's equal to the change in momentum. That's an important distinction. Next up, we want to take a look at how momentum really works best. The concept of momentum works awesomely when we're talking about collisions, specifically collisions where there are no external forces, where there are two objects that hit each other, and the only forces are between the two objects. We have some interesting things happening. So in this situation, what we've got here is we've got two objects, object 1 and object 2, and they're heading towards each other with some velocity. They collide, and you can see the universal collision symbols there, those lines coming out, and then they bounce away from each other. That's the situation that we're going to analyze at first. So, starting with Newton's third law, this is what conservation of momentum is completely based on. The force of object 1 on object 2, notice that's a force on object 2, will be equal to the oppositely directed force of object 2 on object 1. That's a force on object 1. Now, the delta t, the time that they collide, well, the time that 1 collides with 2 is the same as the time that 2 collides with 1, so that delta t will be the same for both objects. You can't have object 1 touch object 2 without object 2 touching object 1. So what we end up with is I'm just going to multiply both sides of this relationship by delta t, because the delta t is the same for both. And you'll see that this is kind of what we just did over here. If you take a look back over here, notice that F delta t is the change in momentum. That's how we're going to connect this with momentum. And here is our, notice that we're going to call this, because this is a force on object 2, this is the change in momentum of object 2. This is a force on object 1, so this will be the change in momentum. It's negative because of that negative sign, the negative change in momentum of object 1. And I'm just going to rewrite this. Delta P2 is the momentum of 2 final minus momentum of 2 initial, and delta P1 is momentum of 1 final plus, or it's momentum of, it's negative of P final minus P initial. So that's what I just distributed the negative sign right there. And then you could just rearrange this to get this expression right here. And this is kind of the most important. This and the one following it are really the bottom line of this whole thing. So this right here, this is kind of the fundamental statement that gives us this. Notice that this is P2 final and P1 final. That is the final momentum of all the objects in the system. This is P2 initial plus P1 initial. This is the initial momentum of all the objects in the system. What this is telling us is that the momentum final is equal of the system is equal to the initial momentum of the system. So that is what we call conservation of momentum. Momentum is always conserved if there are no external forces. It's always conserved. Again, as long as there's no forces from the outside changing the momentum, it is always conserved. This is not true of energy. The most common misperception is that energy is conserved, or mechanical energy is conserved in collisions. It is rarely conserved when you have macroscopic objects. But momentum is always conserved when there's no external forces. So if you got a collision of two masses, it's very likely you're expected to use conservation of momentum to analyze that system. Now, whenever we have two or more particles in a system interacting, their total momentum is a constant. So it doesn't even matter how many particles you have, the momentum of the system will be a constant. And that is as long as there are no outside forces, you will have constant momentum of a system. You can have these particles bouncing off each other like crazy, but as long as all those forces are internal, in other words, between objects in the system, the net momentum of the system will be constant.